Alright, in this video I want to talk a little bit more about the Laplace transform and give the definition and actually calculate the Laplace transform of a function. So the definition, the idea is, so we've got a function f of t, and the Laplace transform of this function is simply defined to be, notice we're going to get a function of s after we do this. So the Laplace transform of little f of s, kind of a common notation. The new function, kind of like when you do derivatives and antiderivatives, a lot of times, so if little f is the function, capital F is going to actually represent the Laplace transform. So pretty common notation. The definition of this Laplace transform is we integrate from 0 to infinity, we take our original function, whatever it was, we multiply that by e to the negative st, we integrate with respect to t, and this is going to be for values of s greater than 0. So when you look at this, probably looks out of the clear blue sky. Like most things in math, there's actually a very nice logical reason, where this, there's a place certainly where this definition comes from. Maybe we can talk about it in a different video. But for now, I just want to grind through the mechanics of doing the Laplace transform. Eventually, I'm just going to show a big table of Laplace transforms, but kind of like, a table of derivatives. Let's show how to actually calculate them, though. So here we're going to compute the Laplace transform of the function f of t equals t. So all I'm doing again is I'm just using my definition here. It says whatever function you want to find the Laplace transform of, you just multiply that by e to the negative st. Well, we wanted the Laplace transform of the function t, so well, we have t e to the negative st. And we have to integrate this simply from 0 to infinity. So improper integrals, if you've forgotten improper integrals, because we have this limit of integration as it goes to infinity, definitely have quite a few videos on improper integrals if you need a little refresher. But hopefully this will also serve as a refresher. So the idea is what we do is we replace our infinity with a different variable. Maybe let's call it w. And we're going to take the limit as w approaches, well, infinity, because that was the original upper limit of integration. And then we have to integrate this t e to the negative st dt. Well, kind of off to the side here, I'm just going to make this an improper integral for a second and integrate this. Okay, so the way that we're going to integrate this, okay, so now, kicks in the integration technique. So how do you integrate t e to the negative st? Well, hopefully this looks familiar. Hopefully this rings a bell. We have to do a little integration by parts here. So remember the integration by parts formula. It says the integral of u dv equals uv minus the integral of v du. Okay, so in this integral, I'm going to label something to be u, and I'm going to label something to be dv, and then we'll take the derivative and the antiderivative to get our du and our v respectively. Okay, so again, I don't want to delve all the way into integration by parts. Videos on that as well. So it turns out, in this case, I'm either going to pick the u to be the t, or I'm going to pick it to be the e to the negative st. And in this case, it turns out to do integration by parts. It's best, what we need to do is let u equal t, and then our dv is going to be the e to the negative st dt. Okay, so, well, if we take the derivative of 1t, we'll simply get 1 dt. Now, to get back to v, we have to integrate e to the negative st. Well, when you integrate e to the negative st, we'll get e to the negative st and have to divide that by the coefficient in front of t, which is negative s. And again, all we're really doing here is we're just doing a u substitution. Again, I don't want to get too off track on all the, the background noise on this problem, which is important. It's easy to forget. But we're just letting u equal negative st. The derivative, again, since we're taking the derivative with respect to t, would be negative s dt. We can divide by negative 1 over s. and get an expression for dt. So really we're integrating negative 1 over s e to the u du now, and that's how we're integrating all of this nice stuff to get the negative 1 over s, and then we'll integrate to get e to the negative st. So I'm not going to go through all those steps. If you're in differential equations and you've forgotten some of this integration by parts, by all means, my advice would be pause it, look at some integration by parts, and work through it. So again, prerequisite material. So, but stuff again that's easy to forget. So, all right. So I've got my integral t e to the negative st dt. I'm going to use my integration by parts formula. Okay. So it says we get u times v. So u is going to be t. My v is e to the negative st divided by negative s. So there's my uv. Minus the integral of v, so that's going to be e to the negative st over negative s. And then it says multiply that by du, which is going to be our dt. All right, so far so good here. So we've got, I'm not going to do too much to the first term here. We have t times e to the negative st over negative s. Two negatives make a positive. You could factor out the s. You can treat that like a constant here. And now we're just integrating e to the negative st dt. Well, again, we just integrated that a second ago. That's what we were talking about. So again, the idea is you do a u substitution to integrate this. So, okay, our t, e to the negative st over negative s, we'll just drop that part down. There's our 1 over s that was out front. And we said if you integrate e to the negative st, well, you'll get e to the negative st over, again, negative s. Okay, so normally we get plus c, but we're going to go back to our fact that we were originally doing a definite integral anyway. All right, so what that really says is, it says this original integral, it says what we would actually get is we would have the limit as w goes to infinity. And then we would have, let's see, t e to the negative st over negative s. It looks like we'll get a minus, so we've got 1 over s, and we've got an s in the bottom. That'll give us 1 over s squared. And then we have e to the negative st still left over. Okay, our limits of integration we said were 0 to w, so sorry, it got cut off there a little bit, 0 to w. So now this is what we're trying to compute a value for. Alright, so again, nothing terrible, just using the definition and a little integration by parts. So again, remember we integrated with respect to t, so we're replacing our t's here, is what we're substituting in. So let's do that here. So we would have the limit as w goes to infinity. So now I'm just going to replace all of my t's with w's. So we would have w, and then let's see, we've got e to the negative, let's see, that would be s times w over negative s. Minus 1 over s squared, and then we would have e to the negative s times w. So there would be our upper limit of integration. And then let's see, when we subtract our lower limit of integration, notice if we plug in t equals 0, in our first term, well, if we plug in t equals 0, we're going to get 0 times all this e to the negative st over negative s, but who cares? Since we're multiplying by 0, we'll get 0. And then we have minus 1 over s squared. Okay, and again, I'm plugging in the fact that t equals 0, so we would get e to the 0 power. And recall, e to the 0 power is just 1. Alright, so getting closer, almost there. Now we've got the limit as w goes to infinity. Again, the negative s in the denominator, you can treat that like a constant. So we've got negative 1 over s. I'm going to pull that out front. And then we have w e to the negative s times w minus 1 over s squared e to the negative s times w. And it looks like we're going to get a plus 1 over s squared. Okay, so now we just have to think about our limits as w goes to infinity. So notice in this case, as w goes to infinity, well, w goes to infinity. Excuse me. We would, if we plug w equals infinity into our exponent, we would kind of get e to the negative infinity. We would get e to a big negative number, and that goes to 0. Okay, so in this case, notice you actually have an indeterminate form. Infinity times 0 is going to be a problem where we would have to use L'Hopital's rule. Notice for our second term here, we've got, okay, so negative 1 over s squared. Again, as w goes to infinity, we're going to get e to the negative s times, well, infinity. By definition, remember we said s had to be positive. Okay, so s is positive. So we have a negative number times infinity. Again, that's going to give us e to the negative infinity. So I'm being a little sloppy here with my notation. But as the exponent goes to negative infinity, e to the negative infinity gets close to 0. So this second factor here in our second term, e to the negative s times w, as w goes to infinity, that's going to go to 0. Okay, so all of that part is gone. Now the only thing I'm trying to think about is, well, what happens to w e to the negative sw? Again, if you want to, you could use L'Hopital's rule on this. Remember, when you have an indeterminate product, we basically put one of the factors in the denominator, but we have to change the sign on the exponent. I'm going to leave the w in the numerator, and e to the it'll become e to the, I almost wrote negative, e to the positive s times w. Okay, so if we use L'Hopital's rule in this case, again, now we're treating w like our variable. We would just get 1 on top. We would get e to the sw, and then when we take the derivative of the exponent, again, treating w like our variable, we would get an extra s. Well, again, as w goes to infinity, we've got e to the, you can think about it as being e to the positive infinity times s. Again, s is a positive number. E to the infinity gets big, so 1 over infinity is going to give us 0. So what we've actually shown is this limit as w goes to infinity of w e to the negative sw. All of this is actually going to give us 0 as well. Okay, so really, we're there now. This term is going to go to 0, so that's gone. We already said that the second term is gone. So all we're left here is simply 1 over s squared. And that is our nice solution here. So the Laplace transform of the function t is actually going to give us this this algebraic expression, 1 over s squared.